我来介绍一下那个今天的报告人啊。张永超博士，他的履历很丰富，是在山东师范大学获得学士学位，然后是在原来的中国科学院研究生院，现在叫国科大，现在国科大。原来他有一个物理学院的啊，
对，是
那个张德海的硕士。
我差点去做弦论。
哦，对，他做的是比较数学物理一点。
对，
还好不要去做弦论，做弦论。
我幸亏转行。
哎，还别说，做弦论实际上在欧美没工作，在中国反而做工作机会可能更多一些。
更多一些，因为国内其实各种学派都是相对独立一些，跟西方的啊。然后，他后来又到北大，那个对季向东手下念博士。季向东就把他送出到马哈帕彻那马里兰大学去交换去了。
去学习语。
对，那大类念书。然后是博士毕业之后，他又到理论物理所舒静那里待了1年。其实是先到高农所秦志忠老师那里待了一段时间，3个月是吧？2个月。然后在舒静那里待了1年。然后后来他拿到了那个比利时布鲁塞尔自由大学的博士 offer。他现在就在那里做博士后。他今年暑假7到8月份来我这里访问。我们今天欢迎他做这个报告。
哎，你和与海波有过交集吗？
没有。大家可能对这个我不是工程师，这边又主要是做实验做理论，不太清楚。能用英文？
可以。
Sorry, I can talk in English. And the title is the supernova bonds on some large particles. Here I mean the dark photon and also the major large particles. And this talk is based on the 2 papers. The first one we finished in 2014, and the second one in progress. And the first one is started by the new version of PDG. It's the first citation for the helium photon section in the Exxon section for the new PDG. You can find on the website. And the second one, this is for that photon. And the second one.
下一期的 PD 值又被 CPC 出版，你才把它的影响因子再上一个档次。现在3.7了嘛。如果下一期 PD 值又被他出版的话，它可能涨到5左右。
And this one is for the dark photon. It's a massive photon from an astro-ion heat signature breaking. And the second paper in progress with my colleague in Europe is on the major light particle. Is from system models. For neutrino models. Here's the comments. We first outline what's the motivation for such large particles, and what's the production for dark photon, and is production after production it will decay into some charged particles in some model, and if it decays inside or outside the core and in the mantle or surface of star, we can have different constraints on the mass and missing parameters. And for the method is we are working doing the calculations. When you see first the 2 constraints, one is from the luminosity, one is from the depolarization effects. And that's the figure for the some model particle physics. It's very successful, and we have lots of Finance models to explain all the questions. Finance model for neutrino masses, for dark matter, and also maybe for matter and matter universe, and also maybe some theoretical arguments for the hierarchy, for quantum unification, and for other string theories stuff. And in some particular way, the missing particle in the previous study model picture. the missing part?
Higgs. Nine. Yes. Right. Which one? What's missing?
Higgs.
I put it in the center of it.
Okay.
It's
Okay.
some theoretical particles, maybe. And we may have many well motivated and theories with an actual one-case symmetry if it's broken by some Higgs mechanisms. We can have a massive neutral boson. That's the dark photon. Very simple. And we can in this Bernstein model scenarios, we can connect using the such case symmetries from the Stein model world to the dark world to the Higgs sector, or even something else we don't know. And such dark photons it can explain the mu minus 2, and here this explanation has been excluded by some observations. And here is some other names for dark photon. It can be sometimes called the hidden photon, a heavy photon, massive photon, or even called U boson. Actually, they are the same particle. And sometimes they call it a Z boson with different couplings.
Here, I think it's more about the naming system. Like this dark matter candidate, WIMP is quite popular because they choose the right name, actually. Weakly inactive massive particles. Now if you are choosing this dark photon, sometimes this dark photon can represent a light massive particle. So it's quite confusing. So if you guys could generally think about a new naming system, like considering massless gate boson as a general name for the dark photon, then they might attract more interest from the experimental side. People might push so many new experiments forward and then start thinking about directly detect them.
Give me
That's my personal bias, actually. Like, can you choose dark photon and then propose some new experiments or set up some new experimental proposals? People and more people can be attracted.
Any experiments can propose the dark photon.
There are many
Test.
experiments for searches or neutrinos such hypothetical particles.
Daisy has one already funded, I think.
Here are all these experiments, current experiments and future proposals. See lots of at the neutrino electron beam down experiments and all phase experiments and high energy colliders, lepton colliders and proton colliders, and some other at LHC. Even we can search different channels, and they are sensitive to different primary space. Here is the current experiments constraints for if the dark photon is killed into the thermal particles. If it kills into some light dark matter particles, that will be different, completely different. And here is this blue region is discussed in the paper. Is also
so the color region is ruled out.
Yes, throughout. And also we can see here. Here is we have the alpha regions. It can explain the P-2, the green regions, and also the electron predations. Here it's excluded by some experiments. And this paper it discussed the supernova constraints. Here it's based it's only on the lunatic constraints.
So how do I understand this plot?
Here it's
Suppose if I read the supernova 1987A,
yes.
the blue part, right?
Yeah.
That means the top ones are useless, right? Do I understand right? This is an exclusion plot, right?
All these readings are excluded.
Exclusion, right?
Yeah,
So if
yes.
I read the blue one,
Yes.
the rest is not useful at all. They are all already being excluded. Right?
You mean the blue one?
No, the blue
no,
one, the
so
blue
the-
one excludes everyone else, right?
No,
No.
part of the region.
How do I understand this plot?
Here in the plot, different experiments are sensitive to different regions.
This is a sensitivity plot or exclusion plot?
Exclusion plot. Exclusion.
That means the blue one excludes the green one, right?
Some parts of the green one.
Most part, right?
Epsilon is the coupling constant, right?
Right?
What's the definition of epsilon?
The epsilon
Is that a coupling constant or something else?
is a missing parameter.
Oh, this is
Is the mixing with the photon?
dark photon and standard matter photon.
Yes. Here, epsilon parameter is surrounding.
Yes, it's a coupling constant.
Surrounding.
It's dimensionless coupling constant.
It's a missing parameter. It's not the we multiply the epsilon by the alpha. We can have the coupling is coupling to the sum of particles.
So yes, we don't understand that plot. Right?
Let me come back
Yeah.
to here.
So that means if I trust the blue one, right?
Yes.
That means epsilon 10 to the minus 4 is excluded, right?
6 minus 4.
10 to the minus 4. If I read the blue part only,
Yes.
the blue part,
Yes.
SN, right?
Yes. Only the blue one.
Yeah, if I read that part only,
Hmm?
then the top part is,
It's not sensitive to the top part.
right?
Yeah.
It's not sensitive?
Yes.
Why?
I will explain why it's not sensitive.
Okay, okay.
Here there is, I have an interesting point. I saw an interesting experiment. LSND.
Which one? LSND.
Is that right?
Yeah.
So in principle, if LSND can be sensitive to such a
It's the meson part of the LSND, not the tree.
No.
Because LSND
Okay,
is
okay.
big.
Do we
Has
have
nothing to do
such
with it.
experiments?
LSND charm Norman because they all use meson beams, so that's why the proton beam down
Yeah,
each
yeah,
other.
here is
Yeah, has no connection with nuclear part.
Let's come back to here is the parameters. Here we actually can have this right. Here is micron we can come back with later. Here actually it can be also with to the sum model z boson. And here I have another parameter epsilon z. Here we can set epsilon z to 0 and we can have a pure dark photon in such simple models. And in recent paper by Michael and Yusuf, he studied also the coupling of dark photon to the sum model W boson from coupling to triple scalar to the delta. It's a triple scalar here. We can connect the extra U1 heat boson to the sum of the W's. Here is current experiment. Here the limit is for light dark photon. Its mass is below twice electron mass. It can decay into 3 photons, or it can be a dimer candidate in the universe. Here the Parameter space is the green, is the red region. Here is a non-thermal diametric candidate. Here is a thermal diametric candidate. if it's that photon played a role of that matter. And this reading, other readings are constraints from other observations, and maybe some are from theoretical arguments.
Here, I mean, go to the previous picture. Recently, there are two rumors, right? One is from LHC is about 750
Yes.
GeV stuff.
It's disappearing.
Yeah, it's going down.
Yeah.
Another one is about the beam experiment in Poland or somewhere.
Yes, PV
Czech
neutron.
Republic. I don't remember the country. Yeah, it's about order 10 MeV particle, right? So what about the constraints from your side?
You mean the PV or TeV or
No,
MEV?
MEV.
MEV.
Yeah, it's about MEV. I
Which
mean, in your
experiment?
plot, it's still existing, right? You can see that it could survive in your exclusion plot. In principle.
In which experiment for the MEV?
They are using some nuclear method to trace back the radioactive decay of barium.
I don't remember such.
Yeah, we can check back the reference. I forgot the name of the experiment, but it's the paper was recently published in GIL, and also there was a follow-up work from US side.
If it's about MEV, it could be in this reading. In this plot here is the MEV scale.
Right.
It's about twice electron mass. If it is about MEV, it can keep into at least two electron-proton pair.
Yeah, some people already consider the dark photon case
For explanation of the
Yeah.
such.
of the order 10 MEV new particle, but it's still a rumor side. So,
What's the significance?
well, the significance is very good. In experiment, it's more than 5 sigma, about 7 sigma if I remember correctly. 7 sigma. It's about 7 sigma.
Remember there is something
At
like
least the
this,
PIR
but I
paper
forgot.
claims 7 sigma signal.
I remember something like this one, but I forgot the name.
Okay, that's fine.
Here, the production of dark photon in the supernova core is mostly from brainstorming process, from scattering of it couples only to the charged particles, from scattering of the proton-proton or proton scattering from the nucleon, from neutron. Such processes. And some other subleading processes are the company-like scattering, this one, but it is suppressed by some number densities in the supernova core. Here is here's the main formula to calculate for calculating the emission rate per unit volume. Per unit volume and per unit time. Here the detail file is Kermit space counting both the initial and final states, final particles, and the E is the energy of the dark photon emitted. F1, F2 is the distribution for the initial protons in the car. And this emission rate depends a large number of parameters on the barrier number density, on the temperature in the car, and also on the dark photon mass, and its massing to the thermal particles, the epsilon and its mass. That's the parameter related to the parameters. And for the epsilon parameter, if it's 10 to minus 10, we can produce a large number of dark photon. Because here is enhanced by the large number, the large baryon density in the car. It's a large number. Here this plot is show the dependence of the number is dependent on the temperature. No, it's depends on the mass. If it's beyond the, here we set the temperature at 30 MeV. If it's beyond this temperature, its mass, its production is highly suppressed. We say if it's a bit above 100 MeV, it's highly suppressed. And
Sorry, I didn't follow any. Why did you guys choose supernova explosion mechanism to constrain the dark photon production inside the core? I mean, basically we have two ways to detect signals from supernova explosion, right? One is detecting photon,
yes.
Second one is detecting neutrinos.
Yes.
And the second one already won the Nobel Prize. And here, I mean, what's the clear difference or clear signals we can observe on the Earth? That's why we most care about, right?
And here we assume the dark photon after produced it decays into the electron-positron pairs.
Okay.
And we can have different signals if it decays at different places. If decay in the core the decay products electron-positron pairs it's not easy to get out of the core, and such production and decay are not effective at energy loss. We cannot have strings on the Fermi space. If it decays outside the core, it will open new portal to energy loss. It will carry away some energy from the core. We can use in the observed neutrino luminosity to constrain the missing parameters. That's the second one. The third one is if we have large number of we can produce a large number of dark photons. After decay, if it decay inside the outer layers, such a large number of electron pairs will blow away the outer spheres. We will have some photon signals from such blowaway. And we don't observe such signals due to such explosion paths. And we can explain the Fermi space. The fourth one at the top is the plasma, the electron-positron photon plasma at the surface of the star. And if we have enough, if the number density, the column number density of the electron-positron pairs is large enough, we can have large number of MeV scale gamma ray observations. That's the 3 or 4 arguments for our limits in the paper.
Okay, thanks.
Here is we have a large number after produced the decays mostly into two different cases. One is if it's about MeV scale, it is into two electron-positron pairs. And the second one is if it's below the MeV scale, it is only into 3 photons. And the second one is highly suppressed by it's from the loop effect. If the parameter is at 2 and we can have a decay length at the cosmological scale. In the first case, if the epsilon square, if the epsilon at -10, we can have the decay length at the scale of the supernova size, and thus we can constrain the parameters at 10⁻10, but not at 10⁻3, 10⁻2 such scales. here is the first argument. Is decay outside the core. That's the simplest one. That's the luminosity argument. We can bring here we are sensitive to the 10 to minus 10 reading, but not sensitive to larger Mason parameters. Here, if the Mason parameter is well above such Mason reading, if it's 10 to minus 4, and it decays very fast inside the core, and we cannot have such luminosity, effective luminosity due to the down production of decay.
Ah, okay. So
That's
this
the
side
reason.
is the exclusion, right?
Yeah.
So the white part is accepting, right?
Which part?
The white part
The white part is not
is
excluded.
possible. Okay,
Yes.
okay, okay. I
It's
see.
allowed in.
Now I understand the first part.
So the mass must be larger than
Here, the mass.
electron mass.
Yes, to electron mass. And here is the mass.
Why
is
is
very-
it like that? What's the reason? SPLG.
Why is
Otherwise, yes, the kinematic forbidden. Yes.
Yes. And if it's very heavy, if it's beyond the TV scale, it's too heavy to be produced. And the lower bound is the Mason parameter is very small. It cannot be produced abundantly. That's we can have such readings. And the second argument is from the we assume the dark matter, dark photon decays outside the core, but inside the mantle. As I said, we can have large number and energetic electron proton pairs. They can glow with out spheres. Here is an example. Here is they can overcome the bonding energy, the gravitational bonding energy of the atmosphere and the core. We can let's cartoon plot. Here the bonding energy beyond some radius. Beyond some radius is decreasing.
Here we have so many graduate students. Maybe you can explain a little more about the supernova explosion or the details of this neutron star explosion mechanism. Otherwise, you can't follow. Seriously.
Actually, the supernova explosion is a very complicated process.
Right.
And for the if the star mass is very massive, the mass is at the 10 solar mass or higher.
8
or
about
heavier.
8 point something. I forgot. But there is a limit of the neutron mass, right?
Yes.
Otherwise, if they exceed such a mass
Yes.
limit, they will start explosion. So
Yes.
this is the starting point. And later you can have so many different mechanisms or whatever.
And if it's beyond some about around 10 solar mass, then the gravitational pressure will push the positron and the electron together to form the neutron and emit neutrinos. And then after some evolution of such processes, we can have we cannot and the Fermi gas cannot balance the gravitational force, and then we can have the neutron star it explodes and emits a large number. I remember it's very complicated, and the most of them are carried away by the neutrinos. And maybe at the first few seconds is from the photon emission, and after at that time the neutrinos are trapped in the core, and after that time, neutrinos become free and they flee away from the cores, and then they observe some signals from supernova 1987. That's the basic idea, and I'm not an expert on such a supernova.
Which one arrives at Earth earlier? Light or neutrino?
I remember it's the neutrino.
Or dark light.
This is fully imagination.
If the dark light could arrive on Earth, its covering should be very small. It's highly suppressed. Here we have to calculate two quantities. One is the bonding energy. We have to estimate the thing out of the sphere is bounded by the core of the supernova, and the second one is the energy deposited by the dark photon products in the inside sphere, at the reading outside sphere. And here is the calculations. And the second one is the bonding energy. That's the simplest form from the gravitational the Newton form. And the first one is for here the Q A prime is actually it's energy emitted from dark photon production and decay, and here is the Here we have a factor of we have two factors. One is 0.8. Here is another factor of 1. Here we count the sphere with a radius of 0.8 to 1. Such sphere. Their density is very low density at the surface of the star. And we estimate the energy deposited inside spheres, inside a thin sphere, and we compare the two quantities. And here is we checked the primary dimensions of such calculations and found a factor of 10 for the such mass products that not change too much our calculations, our limits. Here M star is the star mass, the total mass. Delta M is the below the way of sphere mass. Delta M. Here is the reading excluded. It's similar to the luminosity arguments, but they are different. Here in the Y reading are not excluded. It's allowed. Here in the Y reading, the total energy is less than the bonding energy, the gravitational bonding energy. And the third one is we assume the dark photon decay products, the electron-positron pairs, and the photons from plasma at the surface. And if we have a large number of electron-proton pairs, such pairs will decay into pairs of photons, and we can have. And we can observe MEV scale gamma rays. Here MEV is from the average energy of the dark photon. It's at the MEV scale or 10 MeV. react most sensitive to such scale dark photons. And an important quantity here is the optical depth at the surface. It measures how possible for the electron-proton pairs to annihilate into the photon pairs. It depends two quantities. One is the standard model Thomas scattering coefficient, the sigma t. The second one is the column number density of the dark photon. Here, the column number density, it means in one column at the surface, in one unit column, how number of dark photons are in such what's the number of the dark photon in such column? If the column number is higher, we can have larger probability to let the electron-proton pairs to decay into photons. And here we checked the optical depth dependence on the Epsilon parameter and the mass of dark photon. And we found that it has a false power dependence on the Epsilon parameter. One is from the production of the dark photon. Its coupling to the proton is Epsilon, and it's in the amplitude. When squared, the cross-section has a square dependence on the Epsilon parameter. And the second Epsilon square is from decay. To have such electron, positron, photon plasma, we have to let the dark photon decay back into electron, positron pairs. Then we can have a second Epsilon square dependence. Here. And here is the simplest formalism of the such dependence on the optical depth. And we can calculate if the optical depth is larger than 1, we assume the such electron-positron pair annihilation process will occur at the surface. And we can calculate what's the flux at the Earth we can observe from such annihilations. And here is this plot. It shows the experiment observations of the MeV scale gamma rays from the supernova explosion. From supernova 1970 explosion, and we don't observe any signals about the backgrounds. And we can set the limits. Here is the limits we set on the flux. And from such flux limits, we can constrain the primary space. It's also at the 10⁻⁻⁻ scale, or even lower. That's the limits we got for a massive, for dark photon is mass. Is heavy enough to produce electron-proton pairs. And here we combine the three limits in this plot, and they are sent to different regions, to different region of the Epsilon parameter. And it also depends on the mass of dark photon. If it's lighter, they can exclude larger region. If it's too heavy, it's only a smaller region. A second case is for a large dark photon. If it's not heavy enough to produce electron-positron pairs, it is only into 3 photons. Here, its decay length will be at at the cosmological scale in a large primary space. However, for such long-lived dark photon, we can also apply the luminosity restraints because it carries away the energy from the supernova core. We can apply such limits to such long-lived dark photon. And here epsilon is limits on the epsilon parameter. It's not symmetrical to the dark photon mass because it's very long-lived.
But this also means it could be produced by the Big Bang, right?
Produce what?
By the Big Bang.
I don't know.
I think so. If you assume so, then it would be like cosmic microwave background. Shooting is everywhere, right? Right, because you would allow such process at the beginning.
You mean in
At the same time with cosmically microwave background and the radical neutrino.
You mean it decays into the photons and the photons?
Dark photon.
You mean the microwave for the dark photon?
Yeah, I mean it would be the same thing, right? The radical neutrinos. The Big Bang radical neutrinos, Big Bang radical photons, and you would actually have radical dark photons.
That if it's very large, you can have such a radical.
I think so.
And if we have such a large diffusion, we can change the homology a lot.
Yeah, that's what I'm speculating.
Wow.
Did the reviewer ask this question?
No.
No? Okay, alright.
It's not as smart as you.
The other reason might be the constraints from Big Bang theory is so weak than the current constraints that you can just ignore the constraints from the early universe.
One question is how to produce such if it's very light and weakly interacting with small particles, how it's produced in the early universe. That's the problem.
Okay.
It will be very.
If you define different dynamics, then
Yeah.
yeah.
Well, that's a good idea. Here is a second argument for such a light dark photon is mass below twice electron mass. Here we assume we have a large number of supernovae at the cosmological scale, and they all produce the dark photons in the core from the proton from strong processes, and we calculate the cumulative effects of the supernova explosion of the dark photons and calculate how many MeV gamma rays we can observe at the cosmological scale. And we calculate also the primary space. Here the red one is from the luminosity argument, and the blue one is from the gamma ray observations. Here is from the previous page. Here, it depends on the mass of the dark photon. It's because if the dark photon is lighter, we need a larger coupling parameter to ask it decay into the gamma rays, MeV gamma rays. Sorry, it's below MeV. See, maybe some problem in some calculations. Here you see it's but here is I think its energy is above MeV. Here is some calculations arguments for the dark photon, and then let's go to the metron. The metron is a hypothetical particle in neutrino models. The neutrinos may be major particles. We may break the lepton number from the neutrino interaction to some other scalars maybe. We can then break the lepton number from the power coupling of such forms. Here, lepton number is valid by unit of 2. I remember there's a page. Here.
Mahapatra actually has a model of
Yes.
neutrino decay, neutrino decay to major.
It's proposed to the first table is by Mahapatra, physical reference.
And Badger.
And from, if we assume the simplest one, we couple the single scalar in some model to the neutrinos. After the global breaking of the U1P minus L, we can have a massless Gaussian boson. That's the major. And here is, and here in operation, we assume it's a massive particle, and the micron can obtain its mass from Planck effects or from other couplings, coupling to other particles, maybe heavier particles. And here, if it's the Planck effects, its mass to be very small, expressed. But it's from other effects, we can have a massive or even supermassive micron particle. And here in such couplings of the micron to neutrinos, here is you can see it's an effective coupling. And we integrate out all other possible heavier particles, millimeters. And here T is actually our coupling, and it's have some flavor structure. It depends on the flavors. And here is symmetric in the flavor space. And for the let me see. And for the production and decay of the micron in supernova core, it's similar it's not similar to the dark photon. It's produced mostly from the neutrino annihilation for massive micron particle. You can have such processes. And after produced, it gets mostly back into the neutrinos at the lowest order. Beyond the leading order, we can couple also it to photons from Gimpin 5 operators, maybe other particles in the scan model. We assume for lowest order only to neutrinos. It's the simplest one. And we consider the mass ranging from EV to GV scale. But if it's below EV scale, we can have matter effects that may be important. And if it's beyond the GV scale, the micron is too heavy to be produced. And we are doing the calculations right now, and there's some simple scenarios. And in the scalar structure, we have mostly the electron neutrino. Its potential is very high at 100 MeV scale. It's much more than the mu1 and than the mu1 tau neutrinos in the supernova core from the inverted decay. And to calculate the luminosity due to the micron emission, we have to calculate first its mean free path and see how it can fly, how long it can fly before decaying into neutrinos. And it decays, after produced, it can scatter with the large number of neutrinos in the core with the processes of neutrino plus hadron into another neutrino of a different flavor maybe, and plus the hadron particle. And we have to consider the neutrino density. It depends on neutrino density and also on the hadron distribution. Here the neutrino number density is the simplest from drive distribution. And we found that maybe we can use more complicated expressions for the neutrinos. And here is the energy distribution for the hadron particle. And we have to integrate over the energy of the neutrinos, the hadrons produced, and their angle between the two particles. We can have such big part. That's calculating case. And here is the plot. Here in the gray region, here is the within the gray region, the nuclear part is smaller than the supernova core size. Here we assume is the 10 kilometer. And within such Fermi space, the hadron decays very fast into neutrinos in the core. You cannot get out. That's the simplest arguments. But one question is if it's produced very close to the surface of the core, it may be escape easily from the core. That's another difference. And here we can, after calculating the nuclear part, we can apply the luminotic constraints from neutrino observations. Here the origin bands are the excluded region, and only the region, the origin region not in the gray one are excluded. If it's in the gray one, the hadron is short-lived, cannot get out of the core. We can only exclude the G couplings below 10 to the minus 5 to 10 to the minus 11, such a narrow region. That's the preliminary results. Here, second argument is from the deleptonization. And here, as I said, we have the couplings of hadron to neutrinos, which is lepton number violation. It may also violate lepton flavor numbers. And we can do the simple supernova simulations and found we need a minimum number value of such the electron lepton number, the YLE. If it is different from such value, we cannot have a successful explosion for the supernovae. That's from simulations. And we apply such constraints to the left number left number variation, and we can consider the missing parameters. Here we count the numbers of the hadron. It's not very sensitive to the energy, but only to the numbers, to the numbers of the hadron produced. Here is the preliminary result. Here we are, the nuclear has now been finished. We are doing the calculations and updating the sum of the neutrino distributions and also consider the time diminished of such effects. Here the summary. I only summarize the key only can summarize the dark photon constraints. Here in this region we excluded this region combines all these three different arguments. Here is decomposed to the individual regions from different arguments. Here we up here our limits is maybe 30 times better than the blue reading in the mid plot. Here is for dark photon with mass heavier than twice electron mass. Here this one is here that's red line is from our arguments, from the luminosity and from the gamma ray observation arguments. And it will the reading above this dashed line. That's our summary. And we have some open questions. And one is here considered only we don't have a dark matter particle. We assume it decays into the smaller particles. If it decays into dark matter, that would be different. We have some private discussions. And the other question is from other astrophysical observations. From maybe it can get with the microwave in the cosmology, or maybe some other from other stars. And here is from some here are some comments from my collaborators, and there are also maybe there are other dark particles. You can have some stellar neutrinos at either scale or even higher. You can have hadron, the electron particles, or even a lot of dark matter at it's around m scale or higher. That's it.
So, if Juno can detect supernova spectrum better.
Do Juno have such sensitivities?
Yeah, I mean, if the supernova is close enough.
It's at what's the energy scale for Juno?
Energy scale? I think definitely the best one is between 1 and 10 MeV.
100 MeV.
But we can 1 and 10 MeV. But the best. That's our window. That's our primary physics target. But it can measure particles up to GeV.
Oh.
With up to 100 MeV, definitely highly linear and very good energy resolution. Beyond that, it's a little bit non-linear. So, if we are so lucky,
I
we
think
have a
we can
supernova.
observe something from supernova explosion.
What improvements do we expect?
If we can have the next small explosion, I think we can observe something in Juno. Maybe we can observe the neutrinos, or maybe from other hypothetical particles.
Yeah.
And maybe dominant arrows. And maybe I remember there's a paper from Pingu. They are also to have some sensitivity to supernova explosion.
Their energy threshold is much more higher.
Yes, but in that paper, in the abstract, they said they have some sensitivity to this supernova explosion. I can ask them.
They are definitely.
Maybe some other neutrino experiments. And and I'm creating with Parquet on some other left-right models to consider a massive round neutrino diameter.
So at micron, actually, does it affect neutrinos probability?
If it's light, I think it will affect. If it's coupling to neutrinos is light enough, I think we have some effects on the double PTK. And I don't know, we can check the Fermi space. It depends largely on maybe on the couplings and also on the snaps.
Yeah, because now we don't have a signal.
So here, if the coupling is very small, it's slightly suppressed, it can be collected. If it's high, if it's I think -2 or even some side scales, we can have some effects on double BT, I think. In the theoretical aspects, it can have any arbitrary mass in principle. It don't have any limits.
Yeah.
我先预告一下，下午还有一个报告讲 Life Y model 编码发烧，大概有6到7段文都讲这方面的。
Left right。
对，文章比较多，就是其中一个文章是下一步的 FCC Double H 的一个yellow report， 其中我们贡献其中一个章节。
Left right，李先生的呀。
对，他就是我在那里，就在那个空中心那边那儿毕业的嘛。就知道北空中心那里。我们这代 model 已经做了
10年了。
那我做的大概是，应该在做第7篇，大概是。很多，做了很多，内容也比较丰富，从这个，比如说这个 P 跟 neutrino 到下面都很多东西，到这个 neutrino mass 之类的。
这个超新星棒子的这个实验的可观测量是什么？我看你给我画出的是那个限制的曲线，就是说，你实验探测的可观测量是亮度。
哪一个？这个吗？
超新星爆发那个亮度对它的限制，对吧？那个 loss 我还有一个
不是，你这只是对模型的参数的一个限制嘛？这个实验的可观测量是什么？
实验可观测量实际上挺多了，比如说是这个，像这个里面，比如说我看一个，比如说像这个拍 decay 的话，大概看 decay 产物的这些 shape， 比如说这种它的这个各种这个 momentum momentum 这个 spectrum 之类的，看有没有一个 bump 出来这样子。因为这个你要看它这个，如果你看大图上的话，
那怎么跟你的模型跟那个还有超新星爆发建立起联系的呢？
是这样子的，它这个比如说你要看有一个大图上存在的话，比如说在这个 LVC 上面，它会对某些它肯定要 decay， 大部分 decay 才能看到，就是 decay 到中间就是或是 muse 或是 tau 的话，它decay时候看 decay 的产物的重建，说有没有一个额外的一个势力啊，或者有一个帮手出来。它对某些参数空间是 sensitive， 说10的负3次方的一个 coupling。如果是波诺瓦里面的话，它可能对这部分区域并不敏感，它可能对更低的一个 coupling 更 sensitive， 是这样子的。他们是 overlap， 他们是有一个complementarity 问题，并不是完全中和的。你看这个图里面，很多实验是对这个上面的区域是更 sensitive， 有些区域像斯诺瓦这的话，它是对比较小的伊普斯隆更 sensitive。
下次标上左边是1是
这是我工作不够细致，将来注意。
后来你标了，后来
我自己图案都标了这东西。你这边可能不太容易理解，有这图比较多，里面注意比较多。
我看你刚才有2根线都是一个葫芦的那个图呢，看看，就是2根直线这样子相交。
这个
不是这个，不是这个，好像还有，后面还有，对对对，就是前面那个。到底哪个部分是 exclude 的呢？
这个三个区域里面是被排除的。
只有下面是。
因为这个是被允许的。
哦。
它四块嘛。这个是被标出来的。这话应该做一个标记可能就比较好一些。做的比较粗糙。
What expressions do you use to compare your model and the data of these experiments? Like here you give a list of different experiments on one slide, right? For the cross sections and decays.
Which one?
Where there is a list of experiments. Yeah. Okay.
Here is decay.
So these are your expressions, decay, width, and the cross section which we use for fitting the data to your models, right?
The cross section.
Yeah.
Here we have the. Here is the production diagrams, and we have some of the coupling of the photon to the proton. It can couple to the proton and also electron positron. We can have some cross-sections. We calculate using this formula, calculate this production rate in the curve, and we calculate also its decay. Also the decay formula, and we can calculate the luminosity from the production and decay from the couplings from its mass. We can also calculate the gamma rays produced from the dark photon products annihilation. We have the electron proton pairs from the dark photon decay. And in the star or at the surface, the electron proton can annihilate into two photons. We can calculate the flux of the gamma rays from such annihilation processes, and we can under such class it depends on the dark photon parameters, depends on its mass, on its emission parameters, and we compare the luminosity and also gamma ray predictions to the observations. We have the neutrino luminosity data, and we have also the gamma ray observations from 1987. We compare our predictions. Our prediction depends on the mass and emission parameters. We compare our predictions to the data, and we can between the mass emission in the simple scenario. And it's very complicated. The calculation is not so simple.
So these results are for all of the experiments you listed here.
Sorry?
The result, the constraint which you put on this parameter epsilon.
Yes.
This is from all of the experiments you listed here.
From other experiments?
All of the experiments, I mean. All of the experiments you listed here. Like there were a bunch of experiments on one slide as I saw.
Sorry,
Can you go one slide at the start? I think there is a slide where there are so many experiments you have listed, like charm. Yeah,
yes,
next,
here.
The previous one. Yeah, this one. So you have my question is, you have combined the data from all of these experiments to put constraint on the measure on and the dark photon, this parameter, the epsilon, and the mass of dark photon?
Here we can put the constituency in one plot, and here the constituents are from different processes, but they can constitute the same set of parameters, the mass and the epsilon parameter, and we can combine all the constituents together. And combine them.
I think
And for the
Amir's question is, have you included all of them in your instrument calculation?
All the constraints?
Yeah.
We didn't consider the calculation. We consider some constraints. We calculate only our limits, our constraints, and can put all the constraints together in one plot.
You did not.
No. Sorry. One further, please.
Thank you.
Here the H prime is a light scalar. Here